welcome to this. Oh, I just realized this is actually not correct. So, welcome to homework end of unit review. Um, we are going to go through some problems and I'm going to go through a couple of key points to help you prepare for tomorrow's test. So, linear functions demonstrate repeated addition. Remember that repeated addition is actually multiplication. So, that's why you see multiplication in this equation because it is increasing by 3 each time. If it's increasing by 3 each time, we have to multiply by 3. And so the starting amount here is 4, and this means that every time it increases by 1, the output increases by 3. And so if we were to see in the table, for example, our starting amount would be 4, and then it would be 7, right? So we would do 1 times 3 is 3 plus 4 is 7. 2 times 3 is 6 plus 4 is 10. So see, we're adding 3 each time here. 3 then would be 13. 3 times 3 is 9 plus 4 is 13. All right, so this shows you that it is increasing every time by that 3 there. So exponential functions, on the other hand, are repeated multiplication, and we represent repeated multiplication with exponents. And so the starting factor amount is 4 here. The factor is 3. And that means that we multiply by 3 for every increase of x plus 1. So as x increases, the output is multiplied by 3, and the amount it increases or decreases changes. So unlike our linear functions where we're increasing each time by 3, this one is going to be multiplied, and so therefore the amount that I'm increasing each time, I can't just add a number or subtract a number, it's going to change. So my starting amount is 4. 4 times 3 to the first power is 12. And then 4 times 3 squared is 9 times 4, which is 36. But notice also that each time I'm just multiplying this by 3. But here I'm adding 8 and then I'm adding 24. So the amount I'm increasing is changing. What I'm multiplying by, though, the factor is always going to be times 3. So let's look at some examples. It asks you to label each equation as linear or exponential, and then if it's linear, determine how much it increases or decreases by. If it's exponential, determine the factor. So this one we can see we have a slope here, and it's being multiplied. We don't see any exponents, so this is in fact linear. And our slope is 1,000. That's how much it's increasing by each time x increases by 1. All right. Our next one you can see is exponential. I'm going to abbreviate a little bit here. My factor is 0.9. That's what I'm multiplying by each time. I can also just note that this is decreasing by 10% each time, right? Because if my factor is 90% or 0.9, that means what's remaining is 90%. And so I'm decreasing by 10%, not by a specific amount each time, but by a percent each time. Here, even though this is written differently than this one, this is linear. I could rewrite this as negative 5x plus 40 if I want it in slope-intercept form, and that tells me that, yes, this is linear, and it is decreasing by 5 each time, right, because it's a negative 5. And our starting amount is 40. Our next one is also linear. You might be thrown off because there's a fraction there, but this just means it's increasing by 1/2 each time, right? We're going up 1 over 2 if we were to be graphing this, but it also means it's increasing by 0.5 or 1/2 each time. Not by that percent, but by literally adding 0.5 to each one. And if you wanted to check that, you could make a table and we would have 10 as our starting value. And then I'm adding a half to that. So this next one would be 10.5. Then it would be 11. Then it would be 11.5. Then it would be 12. Okay. The last one here is exponential. You see that exponent here. My factor is also, oh, this is the same problem. Oops. Oh, sorry. But the factor here is also 0.9, and that means we are decreasing by 10%. All right. Problem 2 is a scenario. So if a bacteria starts at 500 cells, is treated with by antibiotic, and decreases 5 cells every hour, this is going to be linear. And we can write the equation as 500 minus 5 times h, or 5x, however you want to write it. But every hour we're losing 5 cells, and so that same amount is decreasing, so it's linear. The next one, a bacteria starts at 500 cells, is treated with an antibiotic and decreases by 5% every hour. This is giving us a rate that it is decreasing by in percent, which means it'll take off each that. So it'll be exponential. We can write this as 500 times 0.95 to the power of x. Now here, the reason I'm doing 0.95 is it's decreasing by 0.05, right, decimal wise, and so what's left would be 95% each hour. The population of Missouri is 5,000, has been increasing by 1/5 each year. All right, so this is exponential. It's 1/5 of 5,000 and then 1/5 of whatever that produces, right? And so this is exponential. It is 5,000. It's increasing by 1/5. That is, in fact, 20%. So 1.2 is my factor because it's increasing. So I'm adding that 1 to my 20% to the power of x. The population of DC is 1.6 million and has been increasing by 1,025 people a year, 1,025 people each year. So 1.6 million plus 1025x, right? It's increasing by that same number of people each year. All right, looking at exponential functions, if we are given something in words and it tells us something is increasing by a certain percent, we have to put that percent into decimal form and then add a 1 to it to find the factor. If it is decreasing, then we do 1 minus the percent because that tells us how much is left. So I have this example here for you, just as a reminder, right? We also saw that in the example above. So let's look at the first problem. Mr. TC puts $1,000 into a savings account that earns 4.3% interest per year. So it's growing 4.3%. 4.3% in decimal is 0.043. And so my factor is 0.43 plus that 1, right? So here then, 1.043 to the power of x is my equation. If Malachi buys a phone for $900 that depreciates 9.2% each year, that means the decimal is 0.092. And so we would do 1 minus 0.092. Again, if you need to, you can use your calculator. 1 minus 0.092, you'll get 0.908 here. So what's left is 90.8%. All right, and that makes sense if we're taking 9.2% off. All right, so then your factor is 0.908. All right, so this is your now factor, so we could say 900 times 0.908 to the power of x is our equation. We know that because 0.092 is what we're taking off, 0.908 is what is left over, right? So 90% approximately of that phone value is left. All right, if we have a table or a graph to find the factor, we look at two consecutive outputs, a little typo there, two consecutive outputs, so one after the other, and divide the later value by the earlier value in the y's. Okay, the outputs. If it is growing, it should be a factor greater than 1. If it's decaying, it should be a factor less than 1, right? So we're going to look at two consecutive values. Look at this one and this one. Doesn't matter which ones you choose, you'll get the same thing. So 64 divided by 512 is going to give me 1/8. We can put that in a decimal form. 64 divided by 512 gives us 0.125. So that is our factor there. Our starting value is 8. So this would be 8 times 0.125 to the power of x. We can see that the numbers are going down. They're decreasing. So this decimal makes sense here because we see that it's decreasing, and it's decreasing pretty rapidly too. So that makes sense. Now, some of you might have told me that we're dividing by 8. That is also true, but dividing by 8 also means we're multiplying by 0.125. That's why I tell you that multiplication and division are very interchangeable. So again, this later value over this earlier value will give you your factor. You can do it with anyone. We could do 1 divided by 8. You can do 1/8 divided by 1. However you would like to do that. You'll get the same answer. All right, let's look at chart number 2. We'll do another one with this one here. So again, we can take any later value and divide it by an earlier value. These two here are nice and easy. 15 divided by 5 gives me 3. That's my factor. It's tripling each time. We can check this one too. 45 divided by 15 is also 3. Works out. Starting value is at 0, so this is 5 times 3 to the power of x. And if we want to write it as a full function, you can write it as f of x equals 5 times 3 to the power of x. All right. Now, our next ones are looking at matching the equation to this graph. So here we see the starting value is 1. All of these have a starting value of 1 because the invisible number in front of those parentheses is 1. So that makes sense. And then we go from 1 to 4, and then from 4 to 16. Right, so this is 2 comma 16, 1 comma 4, 0 comma 1. So to get from here to here and then here to here, we're multiplying by 4. It is quadrupling each time. We can eliminate these because these would be decreasing. They're less than 1. And we can see that it's doing more than doubling, so we know that it is this one here. Similarly here, this time we are decreasing, so we can eliminate these two. And at first we're starting with 16 and then going down to 4 and then 4 going down to 1. So this time we're dividing by 4 or multiplying by 1/4, right? 16 times 1/4 is 4. 4 times 1/4 is 1. So here then our factor is 1/4. All right. Now, if we have something over greater stretches of time, you need to account for the number of times it's happening and then multiply to, or raise rather, to the power of the time that it's growing over. Let's look at an example. The population of fungi covers 500 square feet. Oh, I'm not sure what's happening there. Oh, okay. It grows by 1% each month. That's what's happening. My computer's freezing. And, oh, cool. Awesome. Well, while that's restarting up, it's growing by 1% each time. Oh, all the things are cool. Very awesome. Yay. All right. All right, so sorry about that little bit of a glitch. Let's take a look at this right here. It's saying it grows by 1% each month. How much will it grow in 6 years? Show your answer as an expression and the number rounded to the nearest hundredth. So we have 500 square feet. If it's growing by 1%, it's growing by 1.01 to the power of our months, right? Now, if we're doing this for 6 years, we know that there are 12 months in a year, and then we also then need to raise it to the power of 6 because we're doing it every month, and then we're doing it for 6 years. We're going to do it 72 times. So you can rewrite it. You can write it as this. You can write it as 500 times 1.01 to the power of 72, or you can go ahead and calculate that. So let's do this. We have 500 times 1.01 to the power of 72. Pretty big number. 1023. And 0.55. Okay. All right, the museum has a collection of items that at 20,000, it grows by 2% every 6 months. So in this case, that's twice a year, every 6 months. So 20,000 times 1.02%, or sorry, 1.02 because it's 2%, to the power of 2 because it's every 6 months, so twice a year, and then to the power of 20 because it's talking about 20 years, and we're doing it twice for 20 years, so that is 40 times. So we can also rewrite this as 20,000 times 1.02 to the power of 40, or if you want to go ahead and solve that, which I did request that you do, we have 20,000 times 1.02 to the power of 40, which gives us 44. This is really going wild here. 44. Okay. Yep, there we go. 44,160. All right. Compound interest with nominal interest rate. So if we're given a nominal interest rate and told that something is compounded a certain number of times a year, we need to also calculate for that. And so the standard equation for this is the principal amount times 1 plus the rate divided by time, or the number of times. A lot of times that's written as n, the number of times we're compounding, to the power of n. All right, and then occasionally if we need to multiply by greater periods of times, we would raise that to the next power. So here we have our principal amount, our initial amount is $200. She is going to earn 1.09 as a factor because she's earning 9% interest. It says it's being compounded every 4 months, so we have to adjust this a little bit and make it 1 plus 0.09 divided by, it says every 4 months, which means 3 times a year. Okay, so notice every 4 months, it's not 4 times, that's 3 times a year. And then we're going to raise that to the power of 3. However, it also says she's doing this for 4 years, so we have to raise it again to the power of 4. So now when we write this, we can write this as 200 times 1 plus 0.09 divided by 3 to the power of 12. And we can also calculate, let's do that, 0.09 divided by 3. It's going to give us a nice even number of 0.03. So 200 times 1.03 to the power of 12. And then you can calculate that. So 100 times 1.03 to the power of 12 is going to give us 1. Oh, I did 100 instead of 200. I was like, that's not enough money. There we go. 200 times 1.03 to the power of 12. That's why is 285 and 15 cents. 285 and 15 cents. Now notice that Miss Lee, when I did this, I said, whoa, we started with 200. How come I didn't get enough? And that helped me to find my mistake. So as you're working, that's an important math skill to have, is to check and see, does that make sense? And if it doesn't, go back and look and see what you did, which happens. All right, so a bank charges 2.6% annual interest compounded semi-annually 2 times a year. If Dominic has a loan of 600, so 600, 1 plus 0.026, right, 26%, compounded semi-annually twice, divided by 2, raised to the power of 2, because that's how many times we're compounding it, to the power of 7, because that's the number of years. So we can rewrite this as 600 times. Let's go ahead and figure out what 0.0, that's a lot of zeros there, 0.026 divided by 2 should give you 0.013. So 1.013, excuse me, to the power of 14. Because if he's compounding it twice a year for 7 years, he'll compound it 14 times. So then you can go ahead and calculate that 600. Make sure you put the correct initial amount to the power of 14. And we get $718.92. So does that make sense? He had a loan of $600. He has to pay interest after 7 years. He has to pay back more. That does make sense. All right. So there's a couple examples over here on the side just to show you that if you're compounding monthly, you would divide by 12 and then raise it to the power of 12. And again, you're just dividing that rate by 12 because we're breaking that rate up over a period of time in the year. If we want to find the effective interest rate, we only need to look at the factor raised to that power, right? The new factor raised to that power, and then that gives us our effective interest rate by looking at the percent here. So if we were to look at this as a percent, that can help us to figure out, right? Minus 1, because we added 1 to get our factor, and then that gives us 0.077, which is 7.7%. So in reality, if we were to compound 7.4% over 12 months, it would actually be worth 7.7% of that interest over the course of a year. All right, factors over intervals. To calculate the factors over intervals more than one, right? If it's just one, you apply that later value over the earlier value. Um, uh, Zamara gave us the example of y sub 2 over y sub 1, right? A later y over the earlier y. However, we can also look at wider intervals. And so if the interval is increasing from 1 to 5, it's an increase of 4. So we can look at the factor to the power of the fourth power to see how much we're going to be multiplying by, or what our factor would be in that situation. So you'll see something like this on your test if you have a graph and this is the equation, this is point A, this is point B, and it wants to know what is D over C. Well, to get D and to get C, we can plug in our x values to this equation to figure out what that is. So let's do that. 5.67788 times 3 to the power of 6 divided by 5.67788, remember, because we're dividing here, times 3 to the power of 1. Now remember, these have the same bases. These cancel out because that's just 1. So this now has the same base, so we can do 3 to the power of 6 minus 1, which gives us 3 to the power of 5. That will help you to find out what the answer is. So 3 to the power of 5 gives us 243. And that is your answer. Okay, so again, if it asks you this question, all you need to do is plug in your values for x to get your values for y into the equation. And then you might also recognize that going from 1 to 6 is an increase of 5, which is 3 to the 5th power, looking at that factor there. So let's look at this one here. Same thing, right? This time we're going from 2 to 6. We're increasing by 4. So we can put this as 5.666778. Doesn't matter, times 1.3 to the power of 4, right? In this case here, we are only looking at that 1.3 to the 4th power, because if we were to plug in these numbers, let's go ahead and do that. 5.67788 times 1. 0.3 to the power of 6 divided by 5.67788 divided by times 1.3 to the power of 2. Again, this cancels out. That's just 1. We have the same base here. This would be 1.3. 6 minus 2 is 4 to the power of 4. That is what we estimated to be earlier. And so you can plug that into your calculator. 1.3 to the power of 4. And it'll give us 2.8. 561. Okay. All right, which one is better? So to compare a linear and exponential function, you can put them in the y equals in your TI-84, go to second, then table, and compare those time periods. So let's first start by making an equation for this. After graduation, you're offered 2 jobs. Cedar Grove Associates offers to start you at $30,000 with a 6% increase per year. So 30,000 times 1.06 to the power of x, right? That's a percent increase, so we know that's going to be exponential. So that's one equation. The other equation, Maple Grove, says you get, starting at 40,000. It's a better starting rate, but you get a $12,000 raise per year. So not a percent, but just 12,000 every single year, which means that's a linear function. Which would be better if you stayed at the job for 10 years? And how would you decide which one to choose? So let's put these into our calculator. So we go to y equals, we had 30,000 times 1.06 to the power of x. And then we had 40,000, which initially seems like the better deal, right? Plus 1,200 x, because you're making an additional $1,200 each year. So we're going to go second table and see where that leads us. Well, at first, this linear equation is greater because we're starting with more money, right? We're starting with 40,000. But then over time, as we get to the 10th year, it is now more worth it to be with the first company because now I'd be making $53,000. So if I was going to stay at the job for 10 years, then I would want to choose Cedar Grove. Now my total amount that I'm going to be making is larger. All right, my salary is going to be larger. You may want to consider adding up all of those amounts over years. But if you just want your salary to be greater, we could say Cedar Grove then in this case at 10 years. And then we would probably want to decide that based on how long we plan to stay at the company. Right? Because after 10 years, watch what happens. Look how much more. Here now we're making almost $1,000 more. And as we go up, by my 20th year, I'm now making almost $30,000 more, right? Um, at this point, actually, that's $32,000 more, right? And so by the time I'm in my 20th year, I'm making significantly more money. So if you're going to stay for a really long time, it might make more sense to choose that one. If you're only going to stay for a couple of years and then switch companies, it might make sense to go with the Maple Grove. All right, if you have $200 to invest for 10 years, would you rather invest your money in a bank that pays 7% simple interest? So that's 200 plus 0.7% of 20. So, or 0.7, 7% of 20. So that would be 7% of 20 is 20 times 0.07, which gives us 1.4. So 200 plus 1.4 each year, or would I rather do 200 times 1.05 to get our percent interest compounded annually for 10 years? So I put the 10 in there because we said 10 years. Let's also change this one out for 10 years. And then you want to calculate which one would be the better deal. So you can go ahead and calculate these times 1.05 to the power of 10. We'd make 325, or 200 times 200 plus 1.4 times 10, which you might recognize is only $14, right? So 214. So if we're going to be doing that 7% simple interest, meaning just a straight up 7% of 200, then let me just look at something real quick. Oh, I think that this was calculated incorrectly. I think I put too many zeros or something somewhere in there. It's like, that doesn't look right. That's small. This would actually be 14, which makes it a little bit better there. All right, so 200 plus 140 is 340. So actually, if I'm doing this for 10 years, this option would be better, okay? Because 7% simple interest, let me just show you again because I think that was not clear. 0.077% of 200 is 14. So you'd make an additional $14 each year for 10 years. That would give you 200 plus 140, which is 340. Or if we're looking at 200 times 1.05 for that additional 5% each year for 10 years, we would get 325. So that's a little bit less. So in this case, investing for 10 years, it would be better to do the 7% simple interest, which means that same amount each year. We can also look at this in our calculators to compare. So 200 plus 14x, or 200 times 1.05 to the power of x, and then second table. And if you look at that, you can see that actually after year 10, let's see, nope, this one's still looking a little bit better, but it's around year 15. Around year 15, our second equation, our exponential equation, is starting to look a little bit better, right? After that, it starts to increase more. But if you're only going to invest for 10 years, then that first option, that simple interest option, would probably be better. All right, that's it. Make sure to review, make sure to read, make sure you know all of the definitions for your homework for tonight. And if you have any questions, definitely reach out. I will see you tomorrow. Happy homeworking. Your code word for today is sesame. Sesame.